Okay, so the presentation I want to give today, my talk is about LLMs, like I said before. It's about search engines, and it's about how I started to fear for my job, basically. Let's talk about my job. I'm Zbyszko. I'm supposed to stay in the light, and I was like immediately disregarded that. I'm Zbyszko. I'm a search domain lead at Brainly. Brainly is a company that helps students, young children, learn, basically. I'm also a leader of a Tri-City Joke. So if you're ever in Gdańsk or neighboring areas, come visit us. And first disclaimer, I'm a search engineer, not a machine learning engineer. So I'm a user of machine learning models, I have very little idea how to actually create those and so on. So if you're going to ask me questions about those, all you're going to get is disappointment and my embarrassment. So you can still do it. I mean, it could be fun, but yeah, I can answer any search questions. That's what I really like to do, but machine learning questions, not so much. So, like I said, I'm a search engineer. And who here knows what search engineer does? That's not many people. So search engineering is basically the struggle to get the best results when it comes to given search, like search page and so on. So basically, it's like a constant cycle of hope and disappointment when we try some new solutions, test them in the offline. Then online, we do some A/B experiments, like shown here. Like we are basically going in circles, like for months on end, trying to get like this 5% improvement of results, get a better results in the front. So, and some time ago, in 2022, I gave a presentation on a conference. Actually, that was a Java user group at this point, which was called this way. At search, you say, sounds easy, right? So this presentation is a presentation about search engineering. So since nobody here knows what search engineering is, if you want to know, I recommend seeing this. I never saw this presentation because I'm not watching my own presentations, but I mean, you can. So, but that was not what I was supposed to talk about. After the presentation, I believe that was in Toruń, I was asked the question, do you think that your work will change dramatically considering the rise of ChatGPT? I don't know if you remember this, but ChatGPT, or GPT-3 that changed the game, is quite new, actually. It's not really, I mean, it barely was over a year before it was introduced. And everybody was speaking about this. So obviously, somebody had to ask the question, will ChatGPT change my work as a search engineer, considering that it can answer questions immediately? I mean, it's basically, will this make searches irrelevant? So, yeah, that's at some point it sort of sounded like this. Like I said, what we are doing as search engineers, we are trying to get, we have a list of results, I know, on your web shop or Google and stuff, and we try to guess what do you want from search when you type, for example, fishing? Are you looking for fishing rods or fishing spots or something else? So we're going with a guessing game, and the guesser is actually a computer system. LLMs are much better at understanding. And I love saying that LLMs understand. Many people always point out that's not true, but they're better in understanding what user wants. So, I mean, the question makes sense. Will the work of search engineers change considering the rise of generative models? Sorry for this. So yeah, obviously they can answer anything. I mean, they can answer who the president of US was in 1945, what's merienda. Merienda is a very special word for me. I was looking for a good word to describe Polish thing called podwieczorek. And the general term I got was tea, which I hate. So merienda is the word I'm going to use right now for those kind of things. And obviously it can cure the world hunger, right? So we can ask how to do this, and it knows all, right? So it's solved, right? So I want to answer the question. The question I started with is, generative models are basically the ending of traditional search engines. To understand how to answer this, we must go a little bit back and consider the thing called information retrieval. So the sort of a basis of providing information is actually well described in the books, in papers, and it's a general area of science. The name is information retrieval. And its definition is quite simple. Information retrieval is the task of identifying and retrieving information that are relevant to information need. What is the information need, you ask? The information need is a desire to locate and obtain information to satisfy a need. I love this definition because it's basically using the information need is an information need. So information need is basically you having something in your mind when you start searching. So what I want to propose to you today is to go a bit back when it comes to history of information retrieval and analyze how we've been approaching this in the past and see how we solve the issues related to the information retrieval itself, to searching. So we will be starting with thing called full text search. This is not a complete history. We don't have time for this, and plus I prefer the subjective approach. So we are going to start with this. Who knows what Lucene is? Oh, nice. That's nice. I'm going to give you a crash course in Lucene. After this presentation, you'll consider yourself experts. It will take 4 minutes next, so brace. Lucene works of an idea called inverted index. Inverted index works in a way that instead of like document IDs pointing to some content, we have tokens which come from given documents, which are then pointing to the list of documents they're in. It's called postings list. The process of doing this is deceivably simple. Imagine that you want to have something like this in the index, something that you can then search for. Riding a bike in the middle of winter, that's what we're going to index. First thing we do, we strip it down to tokens. There's a whole process that does this. I will not go into detail here. Then what we do is we put it into our inverted index. This is a new document ID 20, and those are the tokens. So basically, we strip down the whole document, whole content, to basically just a few tokens. You can see here that some basically went missing. We tend not to index tokens like A, in D, and so on, as a very commonly appearing words. They do not add to our understanding of the document, so we are mostly removing them. We also tend to change the form of the words to, like, whenever you write ride, riding, road, and so on, you should always get ride. That's what we do. And that's how the index is constructed, and it's updated. So we can see that the new document appeared here, and we have new, our document frequency was updated. That's it. I mean, you basically know how Lucene works now. How do we query? And this is where we want to meet our information need. What bikes are the best for riding in the middle of January? We basically do the same thing. We again strip down to tokens, and then we find those tokens in the tokens list, retrieve those, and then we have our answer. And obviously, document 20 fills that quite well. You can see that that was the original, that was the query after the stripping, and we couldn't find any mention of January, but we did find bike right in the middle, so success. But this is where it gets tricky. We didn't actually understand in a way and didn't present any semantic meaning behind the original document or the query. So if we look for something like this, we will find the same document, which makes no sense because the original document was about something completely different. So the issue we had for the long time about when it, for the long time was to how do we represent semantic meaning and search using this. This is obviously a lie. That wasn't the first machine learning revolution that happened. But like I said, it's a subjective story. I'm going to, talk about things that were important to searching from my perspective. And the first, and from my, when it comes to me, I would consider this as a sort of an actual revolution. BERT, or bidirectional encoder representations from transformers, is a machine learning model that Google released in 2018, so barely like 6 years ago. The model itself it was designed to help us work with languages, basically. So this was actually a language model. You could do a lot of stuff with this. BERT is still used, I mean, it's only 6 years. It's quite often used for classification tasks, for similarity. So we can imagine it's somewhat relevant for search. And the best part about this, it actually helps us to create a semantic meaning, or at least some representation of semantic meaning of a given text. So that's something we were missing before. Before we just had like bag of words, that's all. But at this point, thanks to Google, we have a model that allowed us to analyze the text also semantically. You might ask what's the big deal? Why it's so important that somebody released a model? I mean, everybody can like train a model, right? The problem is that, and it's even more true with GPT and similar, is that training a model this size, and this was a big model, it's actually considered a large language model. It required a lot of resources, which basically means money. And community effort for building something like this would be difficult. Fortunately, Google released that, and that sort of like jump-started the whole slew of different models, fine-tuned models, and most importantly for our use case, search engines that could use BERT for their indexing and querying process. So that was quite important. So I want to talk a bit about, I was supposed to remove that, a bit about what makes BERT so special and why does it understand so much out of the language. I like for you to pay attention to this part, bidirectional. So the idea is this: we have like a whole sentence, and we want to be able to represent each word of a sentence in a way it makes sense given the context. What I mean by this: apple can mean a computer company, but it can mean a fruit, obviously. So in previous approach I showed you, there would be no way of determining which apple did actually user mean. But what this model does, it actually helps us to do just that. And to do this, the model is pre-trained with a specific approach. First of all, one thing I hate about this nomenclature is that you pre-train a model, but there is no training a model. There's pre-training and fine-tuning. They sort of like skip the step or something. Anyway, masked language modeling. It basically looks like this. So we take a sentence, we can take a full sentence, and we remove, I believe the number was 15% of tokens from the sentence. In this case, it's just a single word. And ask the model during the pre-training to guess what the word was, based on the context that comes from left and right, or in your case, the way around. That's the bidirectional part. It allows you to take the whole context of a sentence, of a content, instead of like just something from the left to right. So that's how you train this. And it's very important to note here that this kind of pre-training allows you to basically use the given blocks of text without any sort of manual work required for example, labeling them. You just basically can take the whole of Wikipedia, feed it into pre-training. The automated learning system will do what we're doing right now, and you can train the model. And that's actually what happened. BERT was trained on the whole of English Wikipedia. That was around 3.5 gigabytes of text, just text. And that's an example. That's why it's so hard to do this. There's also another thing that in the same time BERT was using to train that helps with the contents of a sentences. It's called next sentence prediction. And in a similar manner, we basically took either the two consecutive sentences from the given block of text or mix them up, like take something from here and then something from here. And it's supposed to predict, sorry that we're not using the word guess, predict if sentence is actually fits the general context or not. Some versions of BERT in the later on sort of like lost this pre-training step. It's mostly down to the fact that not always it's needed for like purposes of the model itself. So let me give you an example. Again, this is something we want to index or prepare a representation of. And what we do here, we tokenize again. This time it's a bit different. Tokenizers for machine learning models are generally tokenizing as is. Geez, I'm again doing this. This is where it gets interesting. Generally, the idea of transformers here is that we need to represent the text numerically. How we do this? We have a giant dictionary, basically. Every single word we can think of, or parts of words, is there. And those are like huge files. And every single word we can think of has a representation. I don't have it shown here, but if there are words that are missing from the dictionary, because it can always happen, models generally try to split it to smaller parts, which are then tokenized. And in the end, we cannot even do this. We basically have a special representation. It's called unknown. It's unknown. And we start with CLS as a starting and pad, and we pad the spaces to some dimension. Once we do this, we need to create a thing called embedding. What is embedding? Embedding is a vector. It's a vector in space that our best understanding of this is that it represents some semantic meaning. And what we do here is that based on the sentence itself, we create those embeddings based on the model from every single of the tokens, and then we pull them all together by some calculation and create a single embedding for a whole sentence or a whole content. That might sound kind of mysterious, but there's a good reason why it's happening this way. It's because of how we use it afterwards. Obviously, there are different uses of BERT, but what I'm interested here in is similarity, because that's how we find things. We basically create those embeddings for every document we want to search, and then we create embedding for a query. And what we need to do, you can imagine this in a 3D space. We find vectors which are close to each other. And those who are closest to a vector we are searching with are the winners, basically. That's called k nearest neighbors. So thanks to this similarity, we can properly represent words like Apple. If the context of a given sentence, Apple is a tech company, it will be treated as such. But if the context is a fruit, it will also be treated as such. Example of how those embeddings work is also here. Basically, you can imagine that distance between tokens in a model is represented in a way that distance between vector for queen and king is the same as between woman and man, for example. So, and why I'm talking about this, the important part about what happened here is that we in open source could actually finally be able to represent semantic meaning in our searches and use them to provide better understanding and in the result, better searches for all. It doesn't work for, not every single use case will work well with this, but we can cover much more ground. So this is, I call this analysis part. Basically, what we get is we have a query. We ask the engine to return something, and we get a list of results, like, for example, 10 results. So that's how searches work today, right? So you get a list of results. If you're lucky, the best one for you, at least, is on the top. If not, you have to find something inside. So basically analyze the results and see which one is the one you need. Hopefully there is one you actually were searching for. Whereas what LLMs currently do, they can synthesize information. They can actually provide you something that you asked for directly, which is awesome. So let's move to the synthesizing part and our second machine learning evolution. And this is the one we are currently living in. I'm calling this generative large language models because, like I said, BERT is actually a large language model. Everybody uses LLM as a generative ones right now, but that's not technically true. But they existed for actually quite a few years already. When BERT was introduced, there were already versions of GPT available. They were not that good as GPT-3, but they were already there. How does this work? Training step or pre-training for generative models is a bit different. They are not using bidirectional approach. They're using the next token prediction approach. So if you really think about this, it's basically like your smart keyboards on your telephones. Like you put something in and it's trying to guess what is the next word you want to write. If you don't train your model to actually respond to commands, it will work exactly like this. I will be trying to predict the next word you would be writing right now, nothing else. There are some special steps to make sure that they can actually answer questions. The fun part about this is, obviously models don't have like creativity or something, right? They're basically networks. That's it. So when the first work on GPT started, or generative models started, the issue was that they weren't really creative. By creativity, I mean the answers were short and quite often didn't make sense. The model in general has to guess what the next token is, and the next, and the next, and the next, and the next. So what's happening is we have like something like this. The sky is, it can be blue with this kind of probability, gray with this, and so on. As long as we selected only the first option, it worked like I said before. So basically, it meant that they will always return the same sentences. Those sentences didn't make sense, and so on. What happened later on is that very smart people figured out how to fix this. And they basically told the model to lie. I mean, not necessarily lie, but what they are doing, they are trying to randomize which token is selected. Instead of always going with blue in this case, there will be more chances for it to actually be gray, or lovely in this case, for example. It's called temperature, generally. The higher the value of temperature, the more crazy it gets. The lower one, the closer to the top it will be. But the general idea is that thanks to this approach, sometime you change the token, go somewhere else, generative models are working the way they're working right now. But important thing you have to remember about this particular thing is that there is no bidirectionality here. There is no context of a whole sentence. It only takes something that's been done from left to right, which is fine for generative models, but it sort of loses some information. And in this case, for tasks like analyzing classification and so on, models like BERT can be better. Obviously, GPT has some old data, but it's still valid. It's a much more difficult task to train. It uses a lot more data. Like I said before, BERT was trained on the Wikipedia text, whereas GPT-3 steals everything and goes everywhere. And they are like going on and on. I mean, basically. You know what's happening. I mean, everybody knows the whole story about copyrights and so on. But to effectively have a model that can work this way, you have to get a lot of data. So we have two approaches here. One approach is about classification, which sort of is around searching. And other approach is around generating speech, basically. Some patterns that look human-like, they can also help you summarize stuff. You would be assuming that if GPT works the way it does, actually probably the first part isn't needed. You can just use GPT and answer any questions. But there are like issues with LLMs, you probably all know, but let's just list them here. Are there any philosophers in the room? No? Okay, that's awesome, because I might lie about something unknowingly, and that would be nice. LLMs don't have a concept of truth. There's some work around this, but generally, when we quite often say that ChatGPT hallucinates, that's not really true, because it doesn't really hallucinate, because it doesn't know that something is true or not. If you really think about this, you start questioning, well, it somehow knows how to answer questions, so it generally knows something, right? And the reason it actually knows something is because of us. Or some things we do, sometimes unknowingly, sometimes knowingly on the internet, and generally speaking to each other. This is Herbert Paul Grice. he died like a few decades ago, and his main contribution to the world of philosophy or world in general are the Gracian maxims. Gracian maxims are a sort of like a de facto contract, a social contract we use while speaking to each other. First one is of generally, imagine that you're asking somebody a question, right? So the question gets answered by someone, and we generally try to, not go overboard with the content we are providing. That's not always true, but quite often. So if somebody asks me how to get to some street in Krakow, we will not start with history of Krakow, right? So this street was built this day, and so on. No, we're just going to like give somebody direction. We try to make the content, at least we try to give real directions. I mean, we assume that we know. I assume that we know how to go there, so we provide truth when it comes to going there. That's the maximum of quality. Maximum of reality speaks that if somebody asks me a question about going to Mariacka Street, I will not start telling them how to get to Aleje Jerozolimskie in Warsaw. That's a maximum of relation. The thing we are talking about is related to the question we were asked. And the last one is maximum of manner. We want to explain things to somebody in a way that that someone can understand. So basically, we try to gauge the way we are speaking to somebody or writing stuff on the internet to the actual recipient of the information. That's the fourth maxim. And thanks to the fact that GPT was trained and other models were trained on the data that is available on the internet, thanks to this, quite often GPT can tell you something truthful. Funny thing is that there are actually tests. It's called, if I remember correctly, social pragmatics. There are tests that test models based on those maxims. So basically, there are like scores for each of those, and scientists verify how good they are in the context of what's happening here. Another issue with LLM is that knowledge is only valid to the moment it was trained, even if it's truthful. That means that it will only answer the questions up to the point it was trained, and training model is hard. I mean, really hard. And even if we got like the newest Llama model right now, it's still been only trained with the data up to 2022. So like 2 years ago. I will have to change this slide. Hopefully not, but I might need to at some point. Fingers crossed. Sorry, no politics. Other thing is that if you're trying to find the answer, there will be no way of ranking those results in a way that, like providing the answer that you want. For example, I know it's winter, so asking GPT what to wear makes no sense because it doesn't know the weather. But if you would be able to provide some information to GPT, you would, okay, so if somebody asks you this, please give them some information, give them something about, like, it's winter, so, jackets and so on. And the last thing is, if you want to have like something around, you want to create a chat with your company with some information that is firewalled at some point, you cannot use GPT for this because it won't know the context of those information. So if you like listing stuff internally, for example, without providing the actual information, it will just not happen. So those are the issues. I already mentioned a few approaches how we do searching and find relevant information. So the idea is to tie it all together. Let's use the models what they were originally supposed to do. One is classifying, the bird classifies, and GPT, and in our case Llama, that's a model from Meta, generates. So the idea is called retrieval augmented generation. This fundamental term basically is actually quite simple. What we do is we have I will try to we have some content, some documents, whatever. We want to, first what we're doing, we are indexing this in the vector database. It doesn't need to be vector, but generally in some place we can search from. Encoders are something that create embeddings. Then we have a question. We also encode this. We go to our previously mentioned vector database. We get results. When we get results, we create a new, we enhance the original question that was asked by a user with the data we retrieved from the database or some search engine and so on. So even before we go to Llama or something, we first go to something else to get some other results and give the context. And then we basically ask the LLM to only provide information based off that context we just provided. Easy. So let's do this. It's super easy, so let's just do this. What we'll be using, I'm giving a very short demo. It will be OpenSearch with KNN fields. OpenSearch is a database, I mean, it's not a database, it's a search engine on top of Lucene I mentioned before. It's a fork of Elasticsearch and generally is very, very often used for search related use cases. We use it, for example. We're going to be using the newest and brightest, basically like a week-old Llama 3 model, so obviously nothing will go wrong. And we'll be serving this from a very nifty tool called Ollama. We'll be using MiniLM. I was talking about BERT for a long time, and now we're not going to be using BERT. I really like some aspects of machine learning, even if I don't understand them. There's this thing called model distillation. And it generally is being done in a way that we want to create a smaller model out of some bigger model. And to do this, we train a new model with help from the old model. So MiniLM is, I think Microsoft created it, is a model that basically was learned by BERT. It has a lot of similar characteristics, and it's actually quite good for, it's smaller, obviously. It's like twice as small. And it's perfectly viable for search use cases. It performs on those tests related to search use cases basically the same or close enough. We'll be using LangChain4j. I know that at least a few presentations probably already spoke about this, and there's one in the same room about this, so I will not go into much details. LangChain4j is a port of a library called LangChain. LangChain and LangChain4j are basically basically a toolbox for LLMs, vector models, and so on. So yeah, let's do something, and hopefully this won't break. I haven't done demo live in a conference for 5 years, so please be gentle with me. Things might not work. First of all, the presentation. Is anybody see? It's visible. It's readable. That's fantastic. Okay, so what we're going to do? The general idea is to have content, index the content, then search for the content, and then create a way of doing this. I decided I will be doing a book chat or a PDF, however you call this. My idea is that I want to take some paper, some books or something, index it, and then be able to ask questions about the book. So that's the idea. How do we do this? First of all, we need embedding model, because we are going with the vector approach. That's a version of MiniLM I mentioned before. What you do, LangChain4j have a few different pre-configured models for stuff like this. And then when we initialize book, what we'll be basically doing is using something, sorry, I haven't actually entered this. We'll be using something called first load document, and then there's, where is it? Show, embedding store. And this embedding store is sort of a layer on top of OpenSearch in this case. It's running, Jesus, I hope I actually remember to run it. On my local laptop here. I'll give some index name. We don't really care what it does at this point. It automatically creates an index that is then viable for searching. You can override this, use your own, create your own approach that combines different ways of searching, but you don't have to do this. That's all you actually need to do. We load something, then this is a fun part. I'm basically indexing a book. as I mentioned before, there are documents, right? And we don't want to like index the whole book inside of a single document. So we need to split this. One of the things that it can do is split stuff recursively. It tries the biggest possible part. If it doesn't make sense, like some sentences don't end properly and so on, it will go smaller. And so on. There are a few different ways of document splitters. If you are not offended by using Python, original library has even more of them, which is fun. But I'm actually offended by Python, so I'm not using this. That was a joke. Python is okay. We have text segments. We embed them and add to our store. What happens in the background? We are basically indexing all. We are splitting the book and indexing the book itself. Okay, let's go back. Then we create a content retriever that's needed for the rack itself. We create chat model. We decide we are using Olama. That's a service I'm running in the background that serves few popular models. It's very easy to install. I definitely recommend this. We define the model we are using from that because it can serve few. Once we did this, we are configuring our retriever. I did a small thing around the retriever to know what content it's retrieved, but generally what you need to do is just provide this in the builder itself. So builder works like this. You have some AI service, which is the interface, and then you create the builder, retrieval. Sorry, bookshop is interface. AI service is like an entry for the whole LangChain thing. You create a retrieval augmenter, which is based on something I did before. It also contains, for the rack purposes, it contains a new prompt. Prompt looks like this. We have provided context information below. That's the content. Give this information. Please answer the question. Don't give the answer unless it's. You can put it wherever here. It's just like it means to make it so that it doesn't invent stuff out of the blue. Obviously, LLMs are like 10 years old and they don't always listen. So be careful with that. How we create this. So let's try this. I already have been running this. So that's my favorite part. I mean, I honestly don't know what it will spit out. Oh, this is, sorry. I have to run this again. Okay. I hope I'm not indexing this again. Here we go. So the paper I inputted there is about a thing called program-aided language. It's another helpful thing for LLMs. So let's ask the question: program-aided language. I didn't actually run this. I was expecting this. That's usually the case. So let's go. Sorry, not this. It's the projects, ragtag. Yes, Docker compose app. And Docker isn't running. I forgot to appease the demo gods today. Sorry for that. I always remember that, but there are different ways of doing this. But one would be to start Docker engine before you start your presentation. That would be a good thing to do, for example. Please don't die. Okay, I'm just going to try this and see if it works. Let's do this again. Okay, what is program-aided language? It found some content, and now it will still start generating. Do you actually see this? Because it's very, very low. I hope you're seeing this. Really? Nothing? Okay. Here we are. Very simple description. It's not very elaborate, but it's there. It's a type of language model that provides scaling language modeling with pathways. Pathways, we're not going to get into this. Let's ask we use the PAL description. So what is PAL? It returns something. Let's wait for generation and wait quickly because we don't have much time. Yeah, it can answer stuff. Honestly, I really wanted this to fail because there was a point I wanted to make here, but unfortunately it worked very well. So yeah, sometimes working very well is not what I want. But what I want to say, and that concludes our demo part. I hope you liked it. I will not be doing this again. Let's start the slideshow. Let's get back to this. So that worked for my case, but issue with this approach is that we still need to prepare good search results. We can, it's more forgiving than a normal search. You can provide some results, and LLMs will get some information of this that makes sense. But there's still this part of the whole process of whole RAG thing is that you have to work on your retrieval. You have to work on the whole idea of what are we going to return, and use the whole, our domain knowledge, search relevance knowledge to craft the results that make sense before you send them back to your GPT. That's not a magical method that will allow you to actually do everything just like flick of a wand. You still need to think about the stuff that you are working on, and you still have to engineer your search results. So the question asked by me year and a half ago that I started this presentation with is, do you think your work will change dramatically considering the rise of ChatGPT? Well, after all of this, I finally know the answer. And the answer is no, not really. Thank you. I left with 7 minutes. That wasn't the plan. Now I have to answer questions. That's 11, right? 10. Oh, 10. No, okay. Were there any questions? Only one question. Does LLM you showed in the demo only? What? Does LLM you showed in the demo used only information you retrieved from search to answer the question? Yes, I hope. I mean, it did. It generally works well, and I actually, you know what? Let's do this. This will fail. Yeah. So I generally told it not to, but depending on the model you're using, and I'm using a smaller one because it fits on my laptop. It will follow the instructions to the letter, and sometimes it will not. Working with LLMs is really wild, right? And if you that's why people are using stuff like GPT, which can be somewhat expensive because that's better. The model I'm using has 8 billion parameters, and the models that you can use on the bigger ones that are available are like 10 times bigger. So depending on some stuff, it will sometimes work, it will not. This is mostly for demo, and in most cases, that's really enough. I mean, if it answers it will answer from a given context, but if it can find something else, that's cool. The best part about this is giving the additional context gives you a much bigger chance that answers you will receive are truthful, because that's how we generally work with LLMs, by creating a bigger context. There is something called few-shot prompting. That's basically about providing additional steps, context of the execution, and so on, that actually helps generative models to produce something that makes sense. I knew that would work. And that's the only question, so again. Oh, come on. Where? Oh, can you share your repo with the demo? Yes, I will. I mean, it will. I waited for this talk to finish, and then I will. Oh, more questions. Jeez, somebody asked this question. I love you. For now, LLM often sucks in math. Why could they predict math results by that learning? Why could they predict? They usually do not. What helps with math results is to give them a sort of a longer process. So break down stuff to the smaller steps, and this way it can more often return correct results. But the interesting thing you can do with math is actually something I showed today. This PAL thing I mentioned, it's called program-aided language, is a way of using, it's one of the few short promptings algorithms, is a way of using generative models in a way that instead of asking a model how to solve a question, how to solve some exercise, some mathematical problem, you ask it to write a program that will solve this. It can do it quite well, and it doesn't have to provide the actual values. You have just a program that solves the issue. And then you use something separate, like Python execution engine or something like this, to execute the program with the parameters from the original question. Then you ask LLM again with the code of the program, with the results from the code execution, to explain the program and show the actual results. So there's a paper called, the actual paper here that I was using is the one that introduced this. And if I remember correctly, there are like huge gains when it comes to like truthfulness of answering a mathematical question. So there is a way of doing this, but honestly, ChatGPT or LLMs in general are not like a computational engine. So I'm not sure they ever will be good at solving math. But this approach allows you to actually, without even showing the user that you did this, and automatically solve those mathematical problems anyway. I hope that answered your question, Anonymous. And thank you for asking this, because I love talking about that one. There are no more questions. So again, a few seconds. Jesus. Yes, you can do this. And for example, GPT provides embeddings, but they're not embeddings. Those are different models than LLMs, actually. You can, from the context, from what the one does and what the other does, that actually the thing about BERT that gives you a huge boost is that there's a whole context considered. Like I showed you before, the training for generative LLMs works from left to right. In case of BERT, it's other way around. Also, one thing I didn't stress out here is that LLM RAG approach allows you to work on the actual, actual search results. So there are like already pre-made ways of leveraging search. You can probably do this. I mean, I haven't experimented with this a lot. I have no idea how models that OpenAI provides work, but there are different models than GPT. They called one we've been using recently is called ADA2, for example. Any more questions? I'm giving 5 seconds. We have still a minute. Thank you, everybody, and enjoy your rest of your conference.